In this video, we're going to take a look at the exponential form of a complex number. So to begin with here, let's just denote the exponential form of a complex number. If I've got the complex number z here, then z is equal to r times e to the power of I theta. Where in this case, r is the modulus of our complex number z here. So r is equal to the modulus of z, and theta here, so theta is the argument of z. So theta is equal to arg z there. Okay. So the question here is now, how do we actually denote, how do we actually derive this result for the exponential form of a complex number? Well, the way that we begin this here is by using the Maclaurin series expansion for cosine theta and sine theta. So we begin here with cosine theta. Then our Maclaurin series expansion begins with 1 minus theta squared over 2 factorial plus theta to the power of 4 over 4 factorial minus theta to the power of 6 over 6 factorial. And we can generalize this result here. If we generalize this here, we get minus 1 to the power of r. So minus 1 to the power of r. We then times that by theta to the power of 2r. Times that by theta to the power of 2r. And we divide all of this here by 2r factorial. So that gives us the Maclaurin series expansion for cosine theta. We now need to do the same here for sine theta. So for sine theta here, we get theta minus theta cubed all over 3 factorial plus theta to the power of 5 over 5 factorial minus theta to the power of 7 all over 7 factorial. And again, we can generalize this result here. What we're going to get here again is minus 1 to the power of r. We get minus 1 to the power of r. We then times this by theta to the power of 2r plus 1. So theta to the power of 2r plus 1. And then we divide all of this here by 2r plus 1 factorial. Okay. So that's the Maclaurin series expansion for cosine theta and sine theta. What we're also going to do here is denote the Maclaurin series expansion for e to the power of x. So for e to the power of x here, we get 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial. And again, you can see where this is going here. So we can generalize this result as x to the power of r over r factorial. Okay. Now what we're going to do here is replace x within this Maclaurin series expansion for e to the power of x. I'm going to replace that with the imaginary number here of I theta. So what I'm going to do now is just make a note here. We're going to replace x with the imaginary number I theta here. Okay. So in that case then, rather than e to the power of x, we're going to get e to the power of I theta. We get e to the power of I theta. And again, just replace any x here with I theta. Okay. We're going to get 1 plus I theta. Obviously, each of these now would be squared, cubed to the power of 4, and so on. So, finish that off here then, we'll get I theta all squared all over 2 factorial. We've then got I theta cubed over 3 factorial, I theta to the power of 4 over 4 factorial. We'll do a few more here just to show this result in full. I've got I theta power of 5. That would be over 5 factorial. If we do one more here, we'd get I theta to the power of 6 over 6 factorial. But like we said, this would keep going on and on. Okay. So what I'm going to do now is expand all of these brackets here. So I theta squared, I theta cubed, I theta to the power of 4, and so on. What this would give me here again is e to the I theta. That would be equal here to 1 plus I theta. Then I'm going to get I squared theta squared over 2 factorial. So I squared theta squared over 2 factorial. Then we've got I cubed theta cubed over 3 factorial. I cubed theta cubed over 3 factorial. We then got I to the power of 4 theta to the power of 4 over 4 factorial. Like, it's a little bit repetitive, but you get the idea. So I do it in full again. I to the power of 5 theta to the power of 5 over 5 factorial. And then finally, I to the power of 6 theta to the power of 6 all over 6 factorial. Okay, and again, this would just keep going on and on. So what we're going to do now is use the fact that I squared is equal to minus 1, and we can simplify this expansion here. We're going to just make a note here. So I'll just use I squared equals minus 1. We can rewrite this here then. So again, we just get e to the I theta. So e to the I theta, that'll be 1 plus I theta, that won't change. So 1 plus I theta. But now if we've got I squared theta squared over 2 factorial, because we know I squared is minus 1, this now becomes minus theta squared over 2 factorial. So minus theta squared over 2 factorial. I cubed theta cubed over 3 factorial. In this case now we could write this as minus I theta cubed over 3 factorial. So minus I theta cubed over 3 factorial. I to the power of 4 here times theta to the power of 4 over 4 factorial. In that case, that would simply be theta to the power of 4 over 4 factorial. Moving on to this one now, I to the power of 5 here. Well, if we simplify that, that would give us I, so we get plus I times by theta to the power of 5 here. And we divide that by 5 factorial. And then finally, we've got I to the power of 6 here. So once we simplify that, that would just give us minus theta to the power of 6. Minus theta to the power of 6 over 6 factorial. Okay? And what we can do now is we can separate this here. We can separate this into the real part and the imaginary part. So if we do that here, we've got e to the I theta again. So if we put the real parts first, we get 1 minus theta squared over 2 factorial. So 1 minus theta squared over 2 factorial. We then got plus theta to the power of 4 over 4 factorial. We then have minus theta to the power of 6 over 6 factorial, and so on. Minus theta to the power of 6 over 6 factorial. And like we said, this would just keep going on and on and on. And what we've also got here is the imaginary parts. We have a factor the I out here. And what we've got for the imaginary parts, we're going to have theta, I theta. We've then got minus theta cubed over 3 factorial. We've then got plus theta to the power of 5 over 5 factorial. And again, this will just keep going on and on and on. Okay? And hopefully what you recognize here now is this part here, the real part, that corresponds to cosine theta here, 1 minus theta squared over 2 factorial, plus theta to the power of 4 over 4 factorial, and so on. So if we just use a different pencil here just to highlight this part is a Maclaurin series expansion for cosine theta. This is cos theta. And this part here, if I do that in a different color, do that in orange. This part here now, in fact, just ignore the part where I've highlighted the I here. So just this part here is a Maclaurin series expansion for sine theta. Okay. That's for sine theta. So what I've actually got here then, for e to the I theta, do it over here, is e to the I theta is cosine theta plus I times sine theta. That's cos theta plus I sine theta. We're running out of room a little bit here, so hopefully we can just about finish this. And this is actually a really important result, this. So this is what we call Euler's relation. This is Euler's relation. Like we said, this is a really important result. Okay. So how does this then give us the exponential form here? Well, if we go back to our mod arg form then, so what I'm going to do is I'm just going to box this off in the top corner then. We'll do this in a different color as well. Do this in the top corner then. So using mod arg form, here, then what we've got is z is equal to r times cos theta plus I sine theta. But we know that cos theta plus I sine theta here, well, that's e to the I theta. So what we get then is z is equal to r times e to the I theta, giving us our exponential form here. So re to the I theta there as required. Okay. And there we have it. So like you can see, it's quite a long result, writing down each series expansion, going into the detail of expanding everything. But like you can see, it is quite a nice result. And it also brings about this really important result here of Euler's relation. Okay. But there we have it. So we're not going to take a look at any type of questions here. We'll take a look at some type questions in the next video. So that brings us to the end of this video on the exponential form of a complex number. So in the next video, we're going to take a look at multiplying and dividing complex numbers.